Okay, we will continue to solve examples by using the slope deflection method. And in this example problem, I will be solving the same problem that we worked on using the integration method. Now let's solve it by the slope deflection. So I will be drawing the same figure one more time. We have a continuous beam, member A, B, D, and I have a truss member in here. Length of AB is equal to 3 meters. Length of BD is equal to 3 meters. And we have a uniformly distributed load, which is equal to 3 kilonewton meter. That's point C. Now let's take a look at this member now. As you see, there is no loading on it, and at this end they are connected to the support, and point B with a hinge or internal hinge, meaning that both ends of this member is free to rotate, or the rotation here on this member is not transferred to that member. So when you think about it, this member can only resist axial force, and by definition that's a truss member for us. And we know that the EA of this truss is equal to EI of the beam in magnitude. Okay, they have the same magnitudes, of course different units. Now we will do discretization first, as we always do. So let's divide the structures into nodes and members. So these are the nodes. Now degrees of freedoms. Now at point A, of course we know that there's rotation. Let's call it theta A. But if I use modified equation for this member, I don't have to calculate the value of theta A, not needed. So that reduces 1 degrees of freedom for me. Point B, there will be translation, delta B, there will be rotation, theta B. At point D, there will be translation, delta D, there will be rotation, theta D. Now at point C, of course, we will have some rotation here, but since we say that that's a truss member, we don't really worry about the rotation at this end or at this end, because all we worry about is the translation, how much translation will I get at both ends of this member. So that's why I'm not showing any rotation here. So according to that discretization, I got 4 nodes, 3 members, and I got 4 degrees of freedom, right? Currently I have 4 degrees of freedom. Now let's draw the free body diagram now. Of course, before doing that, you can argue that we know the moment is equal to 0. There is no resistance to rotation at this end. So we can use modified equation in this member and eliminate theta D. That's correct. But let me draw the free body diagram. And from that, you will see that we actually don't need to calculate that translation and that rotation. Okay. So let's first draw the free body diagram, and then we will come back and discuss the degrees of freedoms. So that's our truss member, that's member AB, node B, that's member BD, and node D. I have a uniform distributed load here and the uniform distributed load here, 3 kilonewton meters, 3 kilonewton meters. Okay. All right, let's come to this member. Let's take a look at this member now. This end is free to rotate, yes, and also it's free to translate. So in other words, what I know here is M is equal to 0 and shear is equal to 0. And when you just isolate this member and you know the forces at this end equal to 0, we can actually directly determine the end moment, which is equal to 13.5 kilonewton meters, and the shear force, 9 kilonewtons. And this node is not connected to any other member, or basically you can just say that you will use these two degrees of freedoms, two unknowns, just to calculate this moment and this shear force. But we actually know them. We know their values because that's a statically determinate member. These ends, moments, and the shears at this end equal to 0. So I can directly calculate what these moments are. So let's come back to that discrete structure, and I can eliminate these two. Not needed. Why we don't need it? Because we can determine end moment and shears from equilibrium equations. And we did. It's 9 and 13.5 kilonewtons. So basically, I end up with 2 degrees of freedoms. So I only need to calculate the value of theta b, and delta b to analyze the structure. Once I determine the values of these two, if I want, I can calculate what this translation is and what this rotation is. But in order to fully analyze, I only need to calculate the values of these two degrees of freedoms. Okay. Now let's go to member BA. So I have a end moment that I don't know its value, MBA, and we have a shear force here, VBA. Now I got 2 degrees of freedoms. For the rotational degrees of freedom, I have to write down a moment equilibrium equation at node B. So sum of moments at B equal to 0. Transfer these moments to B. My first equation is as follows. MBA plus 13.5 is equal to 0. That's my first equilibrium equation. Now for the second one, we forget to write down the forces on this truss member. So according to our degrees of freedoms, we say that delta is in the upward direction. So which causes compression on this member. So let's show the compressive forces. So I have a compression here. This is PBC. Okay, now let's transfer all the forces to node B. This is in the downward direction. 9 kilonewton is in the downward direction. And PBC is in the downward direction at node B. Right? Now, I have a translational degrees of freedom. So I have to write a force equilibrium equation at B. So I'm saying that sum of forces in y direction is equal to 0. So this gives me VBA plus 9 plus PBC must be equal to 0. And that's my second equilibrium equation. Now let's write down the slope deflection or the axial force deformation equation. So I will start from member BC. So that's member BC. So we say that according to our definition of the degrees of freedoms, we have a compressive force on this member PBC. And if you write down the equation for the axial deformation, we find out that PBC must be equal to EA over L, which is equal to 2, multiplied with the amount of shortening, that's delta B. And that's equal to, since EI and EA is equal, in magnitude, I can rewrite this EI over 2 delta B. That's the axial force. Now let's jump to the member AB. And write down the slope deflection equations, because member AB undergoes bending deformation only. And we have a translation of degrees of freedom at the tip of member AB, or at point B. So that's the initial, according to the direction that we define for the translation. It moves in the upward direction. That's delta B. That's the chord rotation. That's the phi angle. And the phi angle is in the counterclockwise direction, so it's positive, and that's equal to delta B divided by 3. Now let's also calculate the fixed end moment. So I'm using a pin at A and a fixed support at B. This pin indicates that this end is free to rotate. Uniform distributed load here, that's 3 kN per meters. Now the direction of the fixed end moment at B, we can determine it this way. We say that, okay, what would be the deformed shape look like is if point B is free to rotate, right? So that's the rotation that we will see if this end is free to rotate. But we are saying that the support will make this rotation equal to 0. Okay? So what should be the direction of the moment that the support exerts on this member? It should be in this way. It should press from the bottom to make this equal to 0. So that's the direction of our moment. That's the direction. That's fixed end moment BA. The magnitude, we can just take a look at the fixed end moment table, and that's equal to WL squared over 8. And when you calculate that, this is equal to 3 times 3 squared divided by 8, and that's equal to 3.375 kilonewton meters. Now I find all the parameters that I need to write down the slope deflection equation. So I'm saying that MBA is equal to, now we will be using the modified equation, 3EI over 3. I got theta B minus the chord rotation plus fixed end moment BA. That's equal to, these two cancel each other, EI in parentheses theta B minus delta over 3. The fixed end moment BA is in the clockwise direction, so I should have minus here. 3.375 is my slope deflection equation for moment BA. Now I also have to calculate the shear force BA. So again, I'm looking at this free body diagram. I'm taking moment with respect to point A. So the moment at A equal to 0, and that's equal to VBA times the length 3 plus MBA minus the moment due to the uniformly distributed load. So let's write it down. Sum of moments at A is equal to 0. This tells me that 3 times VBA plus MBA minus 3 times 1.5 is the moment arm, and that should be equal to 0. Put MBA into that equation and calculate what VBA is, and at the end you will get VBA as equal to EI parentheses minus theta B over 3 plus delta B over 9 plus 5.625, and that's our second equation. And if you go back to the equilibrium equations, we know what PBC is, VBA is, and MBA is, and we can determine or write down these equilibrium equations in terms of theta and delta. So let's do that. Equilibrium equations. Sum of moments at B equals to 0. My first equation, MBA plus 13.5 equal to 0. This gives me EI in parentheses theta B minus delta over 3 is equal to minus 10.125. So that's my first equation. The second equation, sum of forces in y direction at B equal to 0. I got VBA plus 9 plus EI over 2 delta B equal to 0, and this equation becomes equal to EI minus theta B over 3 plus 11 EI over 18 delta B, and that's equal to minus 14.625, and that's the second equation. Now we have two equations, two unknowns, and I'm writing the system of equations in matrix form. EI 1 minus 1 over 3 minus 1 over 3 11 over 18 theta B delta B, that's equal to minus 10.125 minus 14.625. And when you solve this system of linear equations, we obtain theta B as equal to minus 22.125 over EI, and delta B as equal to minus 36 over EI. And we can compare our solution with our previous our results with the previous solution. So as you see, rotation is in the clockwise direction, 22.125, and the displacement is in the downward direction, 36 over EI. Okay, now we determined these two. Now let's try to calculate the deflection at point D. So in order to do that, let's take a look at member BD. Let me draw the undeformed shape of member BD. That's B and that's D. Now we know that this point moved in the downward direction. That's delta B, right? And let's show it this way. Let's say that this will move further, and that's delta D, all right? Now, in the slope deflection equations, we are using the chord rotation. So the chord rotation is, this is the undeformed shape, right? Just rigid body translation, and the difference between the displacement between point B and D is as follows. Let's call this displacement as delta, and by definition that's my chord rotation, that's the phi angle. And according to this figure, the phi angle is equal to, that's a clockwise rotation, so it's minus delta over 3. Okay, and here at this end I know the moment is equal to 0, so I will be using the modified equation for member BD. So let's write it down. MBD is equal to 3EI over 3. I got theta B minus chord rotation plus fixed moment BD. Now the moment BD, we already know what it is. It is 13.5 in the counterclockwise direction. So this one is equal to 13.5. These threes will cancel each other, EI. Now theta B, we already calculate theta B as equal to minus 22.125 divided by EI. And the phi angle is minus delta over 3. So plus delta over 3. And the fixed moment BD is plus 3.375. And the only unknown in this equation is delta. And when you calculate that, we find delta as equal to 96.75 over EI. So this is not the deflection at D. This is not the total deflection. It is just the relative deflection between point B and D. So in order to calculate delta D, I have to add delta D is equal to delta plus delta B, which is equal to 36 plus 96.75 over EI, and that's equal to 132.75 over EI. So that's our total deflection. This is 132.75 over EI, and this delta or this distance is 96.75 over EI. Now if you want to calculate the rotation at point D, then you can actually write down the classical slope deflection equation, which is equal to MBD 2EI over 3 to theta B plus theta D minus, or just write as delta 3 times delta over 3 plus WL square over 12. So in that equation, we know what MBD is. We know what rotation is. Now we calculated what delta is. This is known, so this is the only unknown. And if you do that, you will obtain theta D, whatever the value is. Now let's compare our results with our previous solution. So this is what we have in our hand. And as you see, it is the same translation.